and welcome once again to Prof. Dan Tutorials. Please kindly subscribe to my YouTube channel. Thank you. Our topic today is changes in dimension. Changes in dimensions. Roughly, what are we talking about? For example, if you have this figure, let's say you have this figure, and you have a similar figure, but in this time it has increased. Okay, yeah, the two figures look similar but different in dimensions. That is, in terms of the size. Let's say from year to year is 2, but from year to year has changed to, for example, let's say 4. But the two figures look similar. That's what we mean by changes in dimension. Okay, so first, for the sake of this topic, it is very important for us to understand the term scale factor. I depict this by symbol F, scale factor. What is a scale factor? A scale factor is that factor that is used to either enlarge or reduce a figure. Just take note of this. When the scale factor is greater than 1, for example, if the scale factor is 2, is 3, is 4, it means that the figure is going to enlarge, increase. If the scale factor is less than 1, maybe 1 over 2, 1 over 3, 0.5, it means that the figure is going to reduce. When the scale factor is 1, that means nothing changes. The figure will remain the same. Okay? Now, how do you find the scale factor? Let's consider this figure. Let's say this is figure 1 and this is figure 2. These two figures, the geometric name is cube. This cube, this is a cube and this is also a cube. They are similar, okay? And this side of the cube is given as 3 and this length of the cube is given as 6. What is a scale factor? A scale factor, F, is the ratio of corresponding length. What do I mean by that? Ratio, that is, let's say this length is 6. So we have ratio, that is 6 over the corresponding length of this figure 2 to that of figure 1 is this length, okay, which is 3. So the ratio, and 6 over 3 gives 2. So 2 in this case is the scale factor, okay? 2 is the scale factor. That's how you find scale factor. But how do we apply this in changes in dimensions? We are going to look at two areas. One is surface area and the second one is in terms of volume. First, I'm going to use this to explain to you. If you look in depth to this cube, this is a cube. This cube has 6 faces. I have labeled it here. 1, 2, 3, 4. 1, 2, 3, 4 is one face. That's the top. If you look at the bottom part, this is the bottom part, which is 5, 6, 7, 8. Let's look at the sides. We have the right side and the left side. The right side is this portion, okay? That is 2, 3, 5, 8. The left side facing the right side is 1, 4, 6, 7. And we are left with the remaining two portion. If you look at it closely, you see the back and the front. The back is 1, 2, 5, 6, okay? And the front, 3, 4, 7, 8. So this cube has 6 faces, and each of the face have the same dimension. So let's take, for example, just one face. If we look at just one face, which is a square, based on what we are given here, okay, the dimension 3, and this is also 3. How do we find the area of a square? In our previous video, we established that the area of a square is just the square of its side length. So the side length is 3, so 3 squared. This is the area, right? Which simply means 3 times 3. That is just the area of one portion of the cube. But since the cube has 6 faces, so the entire area of the cube, in this case, the entire area of the cube will now be 6 faces, 6 times, or into bracket, the area of one face, which is 3 times 3. Okay? Now, there is something I want you to understand here. Let's look at figure 2, okay? Now, in the case of figure 2, let's establish the same thing. If we establish the same thing, that means that the area is going to be equal to, there are 6 faces into, in this case, the dimension is what, 6 by 6. So just as we did for this, so it's going to be 6 times 6. Okay, please look closely and let's see what I'm going to get out here. I want to transform this area of figure 2 into something like this for that of figure 1. Okay, now this 6 outside, 6 outside. I can have this 6 into, now I have 3 here. This is 6. Okay, 6 can be split into what? 2 times 3. It's going to give me 6. So this 1 6 is 2 times 3. The second 6 is also 2 times 3. So now it's resembling something like this, 3 times 3. So I have this 3 times 3, 2 times 2. So this is the same thing as 6 into, I have 2 times 2, okay, which is 2 squared times, then you have 3 times 3, 3 times 3. In mathematics, if I have A times B times C, regardless of the arrangement, I can still write this as B times A times C, okay? It's still going to give the same thing. So I can decide to bring this 2 squared outside, and that's going to be 2 squared times, then I have this 6 times, then I still have this 3 times 3, okay? 3 times 3. Now, see what I'm trying to do here. Now, this 6 into bracket 3 times 3 is the same thing as what you have here, 6 into bracket 3 times 3. Okay, so that means therefore that the area of the second figure, A2, is equals to 2 squared times, what is this 6 times 3 times 3, which is this, is the area of figure 1. So I have the area of figure 1. And if you look closely, you can write this way, that your area of figure 2 is now the area of figure 1 times, we established that this 2 that we got here, as I did it, the scale factor is 2 for this dimension. So I have 2 representing my scale factor, which I depict by f. So that is f squared. Now, mathematics students, this you have to take note. Regardless of the derivation of this formula, you should know this formula. So what is it saying? It says that when you have 2 similar geometric figures, like this one, they are 2 similar figures, cube or cube, okay? Then the surface area of the second figure is equals to surface area of the first figure multiplied by square of the scale factor. This is very important when you are dealing with surface area. Okay, good. In the same way, we're going to look at volume. When you are looking or considering volume of similar figures, okay? The advantage of this is that when you know the volume of one figure and the scale factor that either reduce or increase it, you can get the volume of the second figure and vice versa. In terms of volume, also, if you do just the same approach, if you do the same approach I've established here, I don't want to do that for this again in order not to waste our time, okay? You will arrive at something like this as well. Just remember that in volume, when you are dealing with volume of a cube, is simply the product of the length times what? The width times what? The height. Okay? It's three-dimensional. So this is volume. So at the end of the day, you are dealing with three dimensions, one, two, three. So you have your scale factor cube raised to power 3. So this is for volume. Volume of the second figure equals volume of the first figure, in which case they are similar, times the scale factor raised to power 3 for volume. Okay, take note of these two formulas. So let's look at an example, very simple example. The surface area of figure 1, this is figure 1, is 20 square meter. So we are told that the surface area of figure 1 is 20 square meter. That is this. Find the surface area of similar figure 2. So this figure 2, we look for the surface area, okay, of figure 2. If its dimensions have been enlarged by a scale factor of 4. So we have scale factor, F in this case is 4. Remember, when scale factor is greater than 1, that means that you expect to get an object that is what? Bigger. So definitely our surface area that we are looking for should be bigger than 20. Simply use your formula. Surface area of the second figure is going to be surface area of figure 1 times the square of the scale factor, because here we are dealing with surface area. And so this is going to give you that of figure 1, 20, times the scale factor has been established as 4 all squared. And this is going to give us 20 times 4 squared, okay, is what? Multiply 4 2 times. So 4 times 4, that is 16. If you use your calculator, this is going to give you 320 meters squared. This is the surface area of the second figure. I hope you understand. Okay, let's look at one more example. Okay, in this case, example 2, we have the figure shows a cylinder. This is a cylinder. Find the volume of a similar cylinder with dimensions 1/3 of the original. This is the original cylinder given. Let's label it 1. We are looking for the volume of a similar cylinder. Another similar cylinder, let's label it volume 2. That's what we are looking for, okay? With dimensions 1/3 of the original. So the dimension of the second figure is 1/3. That 1/3, written in mathematics as 1/3, 1 over 3, is the scale factor, okay, given. 1 over 3, of course, is less than 1. So it tells us that the second figure is going to be smaller. That means it is reduced. It's going to be smaller than that of 1. Remember, we are dealing with volume, and we are dealing with volume, so it's going to be volume of the first figure times the scale factor, in this case, raised to power what? 3 for volume, 2 for surface area. But something in this question is that we don't know the volume of this first figure. This is a cylinder, I will employ you to watch our previous video on how to calculate the volume of a cylinder. The volume of a cylinder, in this case figure 1, is pi square of the radius and height of the cylinder. Please check our previous video. So this is pi times the radius of the cylinder from the center to a circular point is 4. So we have 4 squared times the height of the cylinder is 21. Take note, both the height and the radius are in the same dimension, both meter and meter. So if you use your calculator, you have pi as shift, pi times 4 squared times 21. And your answer is 1055.57. Let's say 1055.57. I'm assuming that the question is asking us to find it to the nearest tenths. Remember, nearest tenths is going to be 1055.6. After the decimal point, one value. You consider the next value, 7. 7 is more than 5. When it's more than 5, it turns to 1. Add the 1 to this 5, it gives you 6. So this is the volume of the original cylinder, which is meter cube. Therefore, the volume of the similar figure is going to be volume of 1, the original, 1055.6 times the scale factor 1/3, that is F, that is 1/3, all raised to power 3. And this is going to be 1055.6 times. Remember, in mathematics, when you have, for example, A over B raised to power 3, it simply means the numerator and the denominator both have this power. So this is A raised to power 3 over the denominator B raised to power 3. Okay, if we follow that here, so that means we're going to have 1 the numerator raised to power of 3 over the denominator 3 raised to power of 3. And of course, 1 raised to power 3 is simply multiply this figure 3 times 1 times 1 times 1, which is 1. So this is 1, and 3 raised to power 3 is going to give you 27. So this is finally 1055.6 times 1/27. Please press your calculator and get your answer. You have 1055.6 times 1/27, which finally gives, in decimal, you have 39.06. 39.06, which can be written in tenths as 39 to the nearest tenth, 39.1 meter cube. I will advise you to solve more questions. I will also advise that you can take the video back without the solution and try to solve it yourself. And when you finish solving, you cross-check again to see if it's the same. This is how you build yourself. Look for more examples online, anywhere, and solve more questions. I wish you all the best. Please subscribe to my YouTube channel. Thank you. Bye-bye.